Right, it is time. Okay, it's time for the next homework assignment because I noticed that last time there was no homework assignment and very few people actually went to the lab. So it's time for the next homework assignment. So it's already up there. It is Find It 1, which is different from Find It version 1 from last year. Similar, but not the same. So we'll go ahead and take a look at Find It. And then we'll use it as a lead-in of tonight's topic, okay? Because I'm pretty sure that some people will be paying attention because of that. Okay, so here we have the Find It homework assignment, which is about the same as the one from last year or last semester. Anyone who wants to get a head start, can definitely watch the video from last year. Because if you can watch that video from last year and be able to do it, hey, it's okay. It's okay with me. All right, so we'll go ahead and get started with this one. And I just noticed that I typed something wrong. It's not going to be a big issue. I just want to fix it so that it doesn't become a point of confusion. The name of the file is findit1.tar.gz instead of just findit.tar.gz. I just want to make sure that that is clear. All right. And so I'm going to download a file, so this way we can take a look at the file and also the what you're supposed to do. It's a tar.gz file. The intention is to untar this or uncompress it in Linux. So it is not intended for Windows. If you have a Windows machine, you can still open it up. Only if you have 7-zip or some other utility program installed. Windows natively does not know how to deal with a tar.gz file. Okay, but that's not intended for Windows anyway, so I'm hoping that nobody is going to try to open this up in Windows. So what you need to do is to get this file onto your Linux development machine. It can be a virtual machine, you can have Linux already installed on the box or whatever. But you have to get it onto the machine into the home folder of where you do your homework. So that would be the account with your last name. And there are several people, or there are 2 last names in this class with a collision. So if it is possible, you might need to add an extension to your last name with a single letter. If you know how to do it. If you don't, that's probably going to be okay too, because I know exactly which 2 name has that issue. Okay, so we'll go ahead and take a look at this file. And and when the system is opening the file, I'm just going to read this note here. Right-click and download this file, which is something that I just did. You have to do everything using your homework account, not root or the default user account. You need to copy this file to the home folder of your homework account. Once copied, run the following command in the same directory. So this is the command to run to unzip the tar file. This creates a folder named findit1 with a single file findit1.s in it. Your job is to replace the underscores, basically the underscore symbol, with direct memory operands so that at label test here, a particular value specified in the file is going to be in register EAX. Warning, your job is to change the underscore to direct operands. Do not make any additional changes to the program. You are allowed to add comments to the file if you find it helpful. When you're done, execute the following command when findit1 is still the current working directory. So this one you have to fix it to findit1 instead of just findit. tar czvf tilde findit1 done.tar.gz space -c uppercase space /space backtake pw backtake. Same kind of command as last time. So I'm hoping that most people are getting this command now. One way to really see it, is to copy and paste it into an editor with a fixed size font. Then you can really see, what those letters are and also where the spaces are supposed to be. This creates findit1 done.tar.gz in the home directory. This is the file that you need to turn in Moodle. And as a tip or hint to myself, these are the things that we need to go over today so that you can do your homework. We need to talk about the i386 architecture being a little endian processor. Okay, this is something that we have not talked about, and today is a good time to talk about it. The X command of GDB can be used to examine memory locations. We talked about it a little bit last time, so today what I'll do is I will demonstrate how to use it in various ways, and you have to figure out how it will be useful for your homework assignment. the print command of GDB can also be useful because even though IREAX can display the content in EAX, it's only going to display it either in hexadecimal or signed decimal. Okay. In this case, you might need some way to print it in unsigned decimal or some other way to get the homework done. Memory allocation in assembly language programming is contiguous and guaranteed. In other words, when we allocate storage, .int, .byte, .word, we'll talk about those today as well, they are all contiguous. Okay? In other words, one allocation is followed immediately by the next allocation. There's no such thing as a variable in assembly language programming. So the barrier in your mind between variables should disappear, should dissolve completely in this class. Okay, so in this class, you don't talk about variables, this variable, that variable. No, we know labels, that's it. Okay. You can perform arithmetic operations on labels. I can demonstrate that a little bit. You should be able to do this assignment without a computer or even GDB. It's just going to be a little bit more tedious. In other words, this homework assignment is doable even without the use of a computer. Okay, if you understand the material, you should be able to do it. Now you can still write a program, fix the program, run it to verify your understanding of the material. Okay, so that would be the way I approach this particular homework assignment, is to do it on the dry dock. In other words, do it on paper, and only use the computer and GDB to verify your answer. That would be the best way to do it. If you just sit down and try to use the computer and just kind of mess around, that may not be the best way to learn these topics. But everybody learns differently. I'm just saying that if I were to do the homework assignment, I would do it on paper first. All right? Well, not necessarily paper. You can do it also on a spreadsheet. A spreadsheet is going to be useful in this case as well. And I'll show you guys why that is the case. Are there any questions about the homework assignment? No questions? Yep.
So all we do is change that draft operand.
There are two. Yep. All you have to do is to do that. Which means some people will use the good old AI technique called generate and test. In fact, I would not be surprised if someone in this class has the know-how to write a Perl script to do the generate and test method. In other words, to generate all possible cases and then test every single one and see which one works. That would be helpful to do the homework assignment, not so helpful when it's time to take a test. So you kind of have to think a little bit more long term, like, do I understand the concept enough to, to do the same thing when I'm in a test, when you don't have a computer in front of you. Okay? All right, so let's go ahead and take a look at the file first. Okay, so let me see where the file is located. Where did I download it? I'll just download it again, make sure I know where it's at this time. Okay, it's in the temp folder. So we'll just go to the temp folder with my command line prompt here. So go to temp, and it has this file here, which is findit1.tar.gz. To unzip it is pretty easy. It's tar xzbf, which is extract gzipped. V is verbose, and then F specifies the file. The following is a file name. So we have findit1.tar.gz, and when you run the command, it will just give you some kind of visible feedback of which folder is created and what file is created inside that folder. So what this says is creating findit1 as a folder, and inside that folder we have just created a file, findit1.s. So let's go ahead and take a look at that file. Oops. And GVM, I can use mouse pad because it has a slightly bigger font. So we'll take a look at that. That's the source file. Not too big, it's really kind of a small program. What is kind of really could be confusing is the dot data section. So let me explain it line by line, just so that we know what the program is and where you have to change. This part, we talked about this already. Dot global means whatever is after that, whatever label is after that, should be made known to the linker. That's basically what it's saying. or that label, is what the linker can resolve. Okay, if it's not defined in this file but it's referred to, that means it's telling the linker and say, hey, I have an undefined reference here. Go find where the label is defined in some other file. But in this case, it's saying underscore start is defined in this file and make it known to the linker because the linker will need to know this label. Dot data means switch to the data section or the data segment where you put your variables, things that can change. In this particular program, we are not changing anything, so it's actually okay to put it into .text too, but it's a good idea to put all your data items in the data section and not in the code section. All right. L1 colon is defining a label. In other words, we are basically putting a bookmark here in the data segment and say, hey, this may be of interest. Okay, I might want to refer to this location later on, so we are labeling this as L1. Same thing with the other two label definitions. This is L2 and this is L3. They're all label definitions. .word is a directive. In other words, it is a command not going to be compiled into actual instructions, but it's an instruction to the assembler to say, I want to allocate space for potentially words. Each word is a 16-bit quantity. In this case, I only have one to allocate, and it has the content of in hexadecimal ABBA. ABBA. Yeah. You guys are way too young to know ABBA. When I ask you what is the most famous export of Sweden, some of you will say Angry Birds, others will say Volvo, and some of you will even say Saab, but it's actually ABBA.
Didn't they sell like 20, 30 million or something like that? Something like that.
ABBA? Yeah. They outsold their cars, within a certain period of time. Yeah. In terms of income, not in terms of number. Yep. And then the next one is .byte 0xAA, or AA in hexadecimal. Okay. So now we have how many bits is in 1 byte? 8. That is correct. So we have a 16-bit thing. Now we have an 8-bit thing. And then I define another label here. And then I define a .int. A .int is 32-bit. Okay. So a .int is 32-bit, and that would be this number represented as a 32-bit number, ABBA, AABB. Then I define another label, which is L3, and here we have 4 individual bytes. The first byte, or the byte at the lowest location, starting from L3, is BB in hexadecimal, AA in hexadecimal, AB in hexadecimal, and BA in hexadecimal. So that's how the memory is allocated and initialized. In other words, by the time you have control when you run your program, this part of the memory is going to be initialized as we specify here. I will give you some examples later on, individual pieces to show you, what is a .word, what is a .byte, what is a .int, and how to define a label, and how to examine memory locations. But you have to put things together in order to solve this little mystery. Your program starts in the code section, which for whatever reason is called .text. Underscore start colon is marking the beginning of your code. This is the beginning of your program. There are only 2 really useful words here, or really useful instructions here. The first one is a move long instruction, moving something into EAX as a register. The second one is a move W, move word instruction, moving into AX, not EAX, AX as a register. So those are the only 2 instructions that you have to deal with. And you don't even have to deal with the registers themselves. The only part you can change is this part here, which is an underscore, and this part here, which is also an underscore. Each one can be different, okay? I'm not suggesting that they should have the same answer, so you will have to figure out what to specify in each underscore location. Is that okay so far? Okay, the explanation. The rest is not going to be that important. I put a label here, test here, because I am going to set up my test script to automatically put a breakpoint at test here, so that it will stop, and in my script I will make it print the value of EAX, then I will match to see whether EAX has the value that I'm looking for. If so, my script will automatically say, yes, this works, and if not, it will say, it does not work. So the idea is, you guys can turn in your homework assignment. I download all the files in one shot and run my script in 30 seconds. I will have all the scores available. Then I will just have to spend the time to manually put it back into Moodle until I figure out how to do that part automatically. Okay. So test here. So everything in this program you cannot change except for the 2 underscores. Okay. So you can only change the underscores. And you cannot change the operand. You must use direct operands and not immediate operands, because it would be pretty easy to do it without
just
direct memory. Yeah, that would kind of defeat the whole purpose of this assignment. So here, when I test your program and put a breakpoint here, when it stops at the no op instruction, register EAX should have a value of blah 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 blah. Okay, that's in decimal. Okay, that number is in decimal. These are in hexadecimal. So it is up to you to choose how you want to do the base conversion and how you want to look at the number. Does it make more sense to look at the number in decimal, hexadecimal, binary, or octal? It's entirely up to you. I give you the tools, you choose which tool to use to solve this problem. Are we doing okay so far with this homework assignment? Yep.
You say you must use direct operands?
You must use direct operands, which is the operand mode or addressing mode that we talked about last time. And we'll talk about that today too, because there will be some examples that we'll talk about today. All right. Are there any questions here? If there are no questions, I will leave this one up because I'll go back and refer to this from time to time just to make sure that I cover all the topics that you need to know in order to do this homework assignment. All right, the first thing I need to do is to talk about what is little endian versus big endian, okay? So what I'll do is I'm going to write a sample program, okay, and we'll use that sample program as a tool to illustrate these concepts. So let's make a directory for today. It's 2014-0220. Go, and I'll just say endian.s. Go. Okay. So what I'll do is I will use the same file to illustrate what is .int, what is .word, and also what is .byte. Those are the 3 directives that you need to understand. So we'll go ahead and do the usual stuff. .global _ start, which is just I explained all these concepts already. So this program is going to resemble your program a little bit. So this time I will have L1 being a .int. I'll just make this 1, 2, 3, 4, A, B, C, D. L2 is a .word. It's 0x. Well, let's pick something that is unique so we don't. It's not possible to mix it up. And then L3 is a .byte. So in this case, it's a .byte. We have used up almost all of them, but not all. So we can use CD here. Okay. So they're all unique now. And then we'll go back to the program part, .text here, and let's see, _ start. I'll do a move L of L1 to register EAX. I'll do a move W, L2 to register BX, and then I'll do a move byte of L3 to register CL. So I'm using 3 different registers here and using 3 different instructions, one to deal with each label. Are we doing okay so far with this program? Okay. And the rest of the program, which I really don't need because I don't see myself going beyond the last instruction already mentioned here, is to exit the program, but it's just good programming practice to also include this part here. Okay, so the last 3 instructions are just saying exit 0. Okay, so you don't really need to worry about those 3 instructions at least for now. Are there any questions about this test program for the time being? What do you think will be in registered EAX? In hexadecimal, it's going to be 1, 2, 3, 4, A, B, C, D, right? Okay. What do you think will be in registered BX? Just focus on the least significant 16-bit of EBX. 5, 6, 7, 8 in hexadecimal, right? And what do you think will be in register CL? CD in hexadecimal. Okay. So we'll run this program just to make sure that these observations are in fact correct, and then we'll go back in and we'll mess it up a little bit, okay? And then we'll try to say, oh, but why is it messed up this way? I know it's going to be messed up, but it's messed up in a really messed up way, okay? So we'll go ahead and take a look later on. Okay, so let's go ahead and assemble and run the program, assemble link and then run the program just to be sure that it is doing what we think it should be doing. AS-GSA stabs and then -o endian.o endian.s to assemble. Link is like that. And then we can now use GDB to take a look into the program. Running this program without GDB is useless. I mean, it has no observable output when you're running it at full speed, so you have to use GDB to look at it. We can list the program to find out where I should put my breakpoint. I'm going to put my breakpoint at the very first instruction. Now, you can say B9 to mean I want to put a breakpoint on line 9, which is the first instruction. You can also say, B_start to put a breakpoint at the label _start. Either one will work. Okay? So for larger and longer programs where the line number is kind of really difficult to deal with, but you have labels where you want the program to stop, you can just say B and then followed by the name of the label where you want the program to stop. It's kind of handy that way. Okay. So that's exactly what I'll do here. Put a breakpoint at _start, and then I'll run the program at full speed. Okay. Now we stop at line 9. We are just about to execute this instruction. So I want to take a look at EAX first, just to make sure that it did not start with the value that we think it should have later on. So we'll say, IR EAX, it prints, it is a 0. Now remember, this is also a place where you can use print. Now when you use print, it's a little bit different. First of all, how do I know how to use print? Help print, okay? Make sure that you understand how to read the help here. Print value of expression EXP, which means it is not limited to printing the value of a register. You can give it a complex expression and it will print the result of the expression. Variables accessible are those of lexical environment of the selected stack frame, blah, blah, blah. That does not apply to us, okay, because we're programming in assembly right now, so it does not apply to us. The $num part is useful if you want to refer to a result that was printed in an earlier print. In other words, you can refer to something earlier, computed earlier, and just say, instead of repeating those 8 digits, I just want to refer to that result. But that's not going to be useful here either. Let's see. The last one is important. Expression may be preceded by /FMT, where FMT format is a format letter, but no count or size letter, CX command, okay, which is the command that we saw the other day. So you want to do a help X here, and when you type help X, I'll just go ahead and identify the portion that is going to be useful. Format letters are octal using O, X for hexadecimal, D for decimal signed, U for decimal unsigned, T for binary, F for float, A for address, I for instruction, C for char, and S for string. Okay, so those are the important things that you need to know about the format part. You can also, when you use the X command, which is not print, but when you use the X command, you can also specify the size. B for byte, H for half word, which is 16-bit, word, which is 32-bit, and giant, which we don't really need to worry about in this homework assignment. So that means I can use a print /X $EAX to print the actual value of EAX, but in hexadecimal. Okay, when you refer to the name of a register using print, you have to precede the name of the register with a $sign to basically say, I'm not referring to variable EAX, I'm referring to register EAX. You do not use the $sign when you use the IR or info register command. Are we doing okay so far? Okay. Well, this is all getting recorded, so if you have any questions or doubts, we can always go back and replay this portion. I will go through every single command that you need to know in order to do your homework. If you want to print something as an unsigned unsigned integer, you can use /u. So that will print it if this is a number that is exceeding 2 billion something in decimal, then it will interpret that number as an unsigned number instead of a signed number. Okay? And that's going to be useful for your homework assignment. Do we have any questions at this point? Yep.
What part of the program is this coming out of? I don't see a label. That you're printing.
That is correct. The only one you want to print using the print command is going to be the register itself.
Because I remember yesterday we were talking about there's only 32 bits in like a set register.
EAX is 32-bit, AX is 16, and AL or AH are 8.
Now if you have more than 32 bits in your program, what's it?
Say again?
Let's say you have more than one register that you're using. Is that
Okay.
not going to happen?
In this particular program, no. In this particular example program, no. Do you want to print multiple registers, or is that what you're asking? If you want to print multiple registers, the only way to do it is to use IR or info register. Then you can give it a list of registers that you want to print. So you can say IR EAX, AX, AL, then it will print the various parts of the same register. But you can also mix and match with any register you want.
So is there a way to select a specific register?
Yeah, you just name it. Because in this case, I named EAX, AX, and AL. So if you want to print EDX, you just say EDX.
So EAX isn't just a standard name that's always used as something you define.
EAX is one of the several registers with that architecture. Okay. Any questions?
The size specifiers, if you're specifying like a 32-bit register and you
Right.
look at like a byte of it, which byte is it giving you?
You cannot only look at one byte. Okay, if you have a 32-bit register and you're using print, then you're looking at the entire register. So if you want to single out a particular byte of a multi-byte register, the only way to do it is to print it out as a hexadecimal number, because that's an easy way to chop into byte boundaries. Any questions back there? Question?
Well, I was thinking about if you're using memory that's not like somewhere farther out of memory, you were using something like 512 bits as memory location, and the program this way. So use something like 512 bits instead of just
But registers, in this case, they're only up to 32-bit. So EAX as a register is only a 32-bit register, and you cannot make it any wider.
I understand. I just meant like how do you designate which other registers you're trying to access? Let's say I want to access number 4.
Number 4.
No, I know we haven't really said anything like that, but let's say you're using 4 different registers.
Right.
Does that ever happen?
And you can only look at each individual register, like EAX, EBX, EDX, ECX, and then EDX.
And those are the only ones we have.
Those are the 4 that we use most often at the beginning of this class, and then later on we'll also add ESP and EVP to the list. Okay. Any other questions? No other questions? So let's go ahead and single step our instruction and then see what happens. So we'll take a look at EAX. And EAX in this is already this is signed interpretation. But if you look at the left-hand side, which is the numbers starting with 0x, that's the hexadecimal representation of the value that EAX has at this point. And it is 1, 2, 3, 4, A, B, C, D, just as expected. Okay, nothing really surprising here. The next instruction is going to load whatever content is at label L2, 16-bit into BX. So that's a single step, and then we take a look at BX here. It is, sure enough, it is in hexadecimal 5678. And then we single step the last instruction, which is loading 1 byte from location L3 to the register CL. So we'll take a look at CL after that instruction, and sure enough, it has the content of CD in hexadecimal, but in decimal, in this case, it is printing a negative number, because by default, IR will only show the number as a signed, using the signed interpretation and not the unsigned interpretation. For this homework assignment, you want to treat everything as unsigned. Okay, so forget about the signed interpretation. To do it as an unsigned number, what you need to do is to use print, do a /u. Do we have any questions?
Just making sure unsigned and signed.
Say again?
I was just making sure the difference between unsigned and signed, but I know what it is.
Just make sure to use the /u format when you want to look at it as a decimal number. So this way, if I look at the same thing, which is register CL, it prints it as 205. We haven't really talked about signed versus unsigned interpretation yet. So at this point, I'm not going to spend too much time to talk about it. But basically what it is you can look at the same bit pattern using the signed interpretation or the unsigned interpretation. The difference is you can only represent so many numbers within, with 32-bit. So the question is, do you want to represent values from 0 all the way up to 4 billion and something? Or do you want to represent numbers from 2 billion something down to -2 billion something? So the signed versus unsigned interpretation is just choosing that. Okay, which range of number do you want to represent? Okay. But in this particular case, in your program, in your homework assignment, always use the unsigned interpretation. Yep.
Why does it have $3? Is that being labeled 3 or has
The $3 is referring to the third print in this process. So that means later on, if you want to say, okay, what is the result of the third time we do the print plus the result of the second time we do the print? So we can do something like that, which is kind of cool.
And then it'll just assign a new $1 every time you do a print command?
Correct. Yep. So that's your kind of log thing. So you can refer to a value that was computed before using print without having to type the number yourself.
If you then change that location, what would happen with that?
It would not do anything to the dollar one.
The
dollar ones
original
are
dollar would stay?
Yeah. Because the $1, 1, 2, and 3, they are all basically the value actually printed in the print command. So changing the locations would not change that. It does not re-evaluate the expression. It simply refers to the result of that expression. Yep.
Why is the answer of those three already activity 1?
Because $2 is 0.
Where's your zero? What's the difference?
Scroll down somewhere. We can't see it right now. Right here. So that's a 0.
You can bring something there.
How would you then print it in unsigned? Because in $4 it printed non-unsigned. Okay.
And you can do the same thing here, which just doubles it.
Okay.
Yep. All right.
Wait, $3 was 205.
That's because they're it's casting this number first to a 32-bit representation first, and that's why we have a problem like that. It's doing an internal cast that we cannot see.
Why it cost a certain bit?
Sorry?
Why it cost a certain bit?
Say again?
Why it cost a certain bit representation?
Because when you refer to $3, I think what happens is because CL is a 8-bit quantity, right? But when you do an addition, what the addition operator wants to do is to use 32-bit natively. So when it sees an 8-bit value on one side, it will say, "Hey, I don't want to deal with an 8-bit number. I want to cast it to a 32-bit number first." But natively, each number is an integer. So when it's casting it from 8 to 32-bit, it's doing the signed extension first, and then it will say, "Oh, okay, you want it as an unsigned number." So we'll explain the signed extension thing later on. Question? Go ahead. Every time you print, that is correct. So you can refer to that result, the result of that print. Only if you do a print. IR does not do that. X does not do that. Okay. Question?
I was just asking about but it's not stored anywhere. It's just something for us to understand.
Which part? Correct. That actually is stored inside the debugger, so it's kind of like a cache thing. So you can refer to the result of the recent print easily. So it's a handy feature, but I have not found it very useful myself. Yep.
If you did just the regular print $3 and plus $2 without the slash u, and then did the print slash u of like say $4, would it show you the actual amount instead of having that problem of print slash u $3?
Okay, that's a good question. The question is, what if I do not use the slash u? The answer is it's going to print -102. Because the numbers are internally signed, so that's why it would cast everything to, but this is going to be a 102, but -102, but represented as a 32-bit number, because that's the native format that GDB likes to use.
So if we did print slash u $6 would show the number $5?
Correct, because that's the flip side of interpreting the same bit pattern, but using an unsigned interpretation. But we are not quite there yet to talk about signed versus unsigned, so that's why I'm going to refer that topic later. Yeah.
Question. So the original value is supposed to be like 4294. Whatever the number right there is plus 102 is the highest number it would go to, the unsigned? The highest number it goes to?
The highest number would be that number plus 101.
101?
101.
So it's because like it's going to an unsigned, so it reverses the process. That's what you're talking about.
We'll talk about that
I'm just
later.
wondering, is that what it's about? Because when it goes over the value, then it goes to the negative of itself.
Kind of. We'll talk about that later.
But that's the concept is, right? That's a concept.
Yes. Yes.
Concept.
Yep.
Because big number always confuse me.
Okay, so let's focus on what you guys need to know to do the homework.
Can you print a
Okay.
number like 10?
Sorry?
Can you print a number?
Absolutely, and it can be any expression. So if you have a complicated expression like 10 times the value in EAX, plus the value of BX times 200, sure, no problem, you can do it. Yep. Okay. Any other questions about the print command? Okay, so no big surprises here. Okay, let's go ahead and mess up the program. Messing up a program in a controlled way is really one of the best ways to learn something. Okay, so I'm not talking about accidents. I'm talking about intentionally changing the program and try to predict what it's going to do and then observe the actual outcome when you run it through GDB. Okay, that's one of the best ways to learn something in this particular class. I don't know about your physics class or chemistry class, because your chemistry professor may not appreciate you doing something other than what is described in the lab procedure. But in this case, I promise it won't break anything. Your PC will not die if you do something like this. The worst case scenario is it will just give you a segmentation fault, which is relatively harmless.
So what is 1 byte?
Hmm?
Byte, bit? What's 1?
Sorry?
1.
The 1, okay,
It's
so
byte
what
one.
is it doing here? Okay, so let's take a look at this instruction. This is the only thing I'm going to do to change this instruction is to say, L1 plus 1 instead of just L1. All right, so I'm moving the cursor out of there so we can just see more clearly. This is L1 plus 1. So the question is, what exactly is it doing? What is the first operand? Now, it used to be L1, which seems kind of clear, where we are grabbing those 4 bytes. So now it is L1 plus 1. So where am I grabbing those 4 bytes to copy to EAX?
Plus 4 bytes come from L2.
Not plus 4, okay? Because in the case of an assembly language, there is no concept of a type.
So 1 is bit or byte?
It's 1 byte over.
Byte, okay.
It's just 1 byte over. Okay, it's just 1 byte over. In other words, we are copying a part of the .int on L1 with L1, starting with L1, and 1 byte that is starting with L2, because we're shifting it by 1 byte. So if you look at how memory is allocated, it's all contiguous. Remember, in the homework assignment, you have to keep in mind that everything is contiguous. So we have 4 bytes allocated first with a .int, with L1 at the lowest portion of it. And then we have a dot word next to it, and L2 is at the beginning of the dot word. And then we have a dot byte, which is the last one, with L3 at that particular byte. This is the lowest part of memory, and this is the highest part of memory in terms of address. Are we doing okay so far with this map? Yep.
Is it always like 1 byte? Is it always 1 byte?
It is always measuring byte. Okay? So L1 plus 1 refers to this location. This is L1 plus 1 as a location. In other words, we know that it's copying these 4 bytes into register EAX. The question is, what exactly will end up in register EAX when I use IREAX or print/x $EAX to print it in hexadecimal? That's the question. What do you guys think? Just looking at the code here, looking at how L1.in is defined and L2.word is defined, what do you think is going to be in register EAX? And I'm taking bets right now.
2, 3, 4.
Okay, go ahead, one at a time.
2, 3, 4, A, B, C, D.
Okay, we have 2, 3, 4, A, B, C, D.
5.
Without 2s.
5.
Mm-hmm.
Okay, that's 1. Okay, any other? Go ahead.
3, 4, A, B, C, D, 5, 6.
3, 4, A, B, C, D, and then 5, 6. All right. Any other takers? Go ahead. Thinking. Okay, thinking is good.
1, 2, 3, 4, A, B, C, D.
1, 2, 3, 4, A, B, C, D.
E.
Huh? Where? E? Here?
No, it's from D. It's from D, E.
Say again?
E instead of D. E instead of D.
E instead of D. So that's D here. Okay? 5, 6, 7, 8, C, D. 5, 6, 7, 8, and then what? CD. And then CD, like that. Okay, so these are all in hexadecimal. Okay, so any other takers?
So, are we going to print signed or unsigned?
In hexadecimal, there's no such thing as signed versus unsigned, because in hexadecimal it's a direct translation from binary. Right. So that's why we don't talk about signed versus unsigned when it is in hexadecimal. Any other takers? Come on.
Int is a 16th bit.
Go ahead. You think the second one is correct? Okay. So I'm going to place my own bet here. Okay, I'm going to place my own bet here, which is none of these. But I don't want to just say none of those because that's kind of like cheating, right? So I'm going to say 7, 8, and then 1, 2, 3, 4, and then A, B here. Okay. And I'll make my name here. Yeah. Okay. So we'll see what happens. Okay. Because it doesn't look likely. I mean, what is the 7, 8 doing here? I mean, it doesn't seem to be connected at all. Okay. So we'll take a look and see, whether it really is going to do that or not. And if it does, I will explain why it is doing that. If it does not, I will still explain why it's not. Okay, but I think I have taught this class enough times to know the correct answer just by looking at it. Okay, but sometimes bad things happen, and occasionally I will be wrong. Okay, so we'll go ahead and take a look, put a breakpoint on _start, run the program. Now we are ready to execute this instruction. So I'll just go ahead and single step without explaining anything, and then we'll take a look at IREAX. And guess what? But why? That is correct. It is a little endian processor. Okay, because when you look at L1 on the .int 1, 2, 3, 4 ABCD, the question is, how are we storing those 32-bit into 4 bytes? That seems to be a pretty stupid question, doesn't it? Okay, how do we store those 32 bits into 4 bytes? Tag 32-bit, 32 divided by 8 is 4 bytes. So why are we having a question here? It's the ordering. Okay, it's the ordering. So, okay, let me just try to explain this part here, but I'm going to use a, let me think. I'm going to use a spreadsheet here just to show you one of the many tools that you might find useful doing your homework assignment. Okay, it's entirely up to you guys to decide how you want to do it, but I'm just going to use this as a tool. Okay, so what we have here is a value of 0x1234 ABCD in hexadecimal. Is everybody convinced that I need exactly 4 bytes or 32 bits to represent that number? Okay, that's the minimum to represent that number. How many bits can be represented by one single hexadecimal digit? 4. Okay, we established that last time. Remember the table lookup thing? 16 entries. Okay. Okay. So now the question is, we know there are 4 bytes involved here. The question is, okay, which 4 bytes do you think are involved here? 1 byte is 1, 2, right? 1 byte is 3, 4. 1 byte is AB, and 1 byte is CD. Those are the 4 individual bytes that we have to somehow arrange in order to represent a number. Are we making any sense so far? Okay. Now, we don't have to specify the ordering within a byte. Okay, there's no need to specify the ordering of bits within a byte because we do not have anything that can shift by 1 bit when we read it. Is that making any sense? Because when we deal with the address, which is L1 plus 1 this time, the plus 1 is at a byte boundary. I can never specify L1 plus 0.5 to shift by 4 bits. That doesn't work. Okay, it just does not. So that's why we don't have to worry about within a byte how do we order the bits. We only have to specify within a multi-byte word or multi-byte integer how do we arrange the individual bytes. Is that part okay? Because I have seen people trying to switch individual digits within a byte, and that part is not necessary. Okay. So what we want to do is to say, okay, we know that L1 is pointing to the first byte. L1 is specifying the first byte of the 4 bytes representing this. So the next question is, if I look at L1 here, and this time I want to list it as individual bytes, what does it look like? In other words, does it look like, okay, I'm just going to do a lazy thing here, do a copy and paste. Does it look like this? Or does it look like the other way around, which is CD first, and then AB, and then 3, 4, and then 1, 2. Those are the 2 choices. Does it look like this? Or does it look like this? First of all, before we go any further, does everybody understand what I'm trying to illustrate here? What are the 2 choices that you can choose from? Okay, we got 32 bits that chops up into 4 bytes. The question is, how are those 4 bytes arranged or ordered in memory when we store the 32-bit number into memory? The answer is the second one. Okay, it has to do with the Intel processor being a little endian processor. Being a little endian processor, the first thing or the only thing you have to remember is the least significant byte is at the lowest address. The least significant byte is at the lowest address. When you write a number, let's not talk about a hexadecimal number. Let's talk about a decimal number, 768. Okay, if you look at this number in decimal, which one is the least significant digit? This is the least significant digit, right? So when you look at a multi-byte number, the least significant byte is going to be this one. Okay. Well, I shouldn't be using this as an example because these are, guesses for the homework assignment. For the example. So in this case, CD is the least significant byte. And because of the little endian nature, it is the one that has the least or the lowest address. So that's why the CD, the byte representing CD in hexadecimal, is at location L1. That's why CD goes here. And then we move to the more significant bytes. The next one is 80. And then the next one is 3, 4. And then the next one is 1, 2. That is how these 4 bytes are arranged in memory in order to specify the value of 1, 2, 3, 4, A, B, C, D in hexadecimal. Are we doing okay so far? Is that okay? So the next one, being a 16-bit value, which I think is 5, 6, 7, 8. So 5, 6 is the more significant byte. 7, 8 is the least significant byte. the next one, we don't have to really worry about it because it is just, which one? CD. It's also CD? Should have used an E now, right?
Wait.
It's okay.
Where
Doesn't
did that come
matter.
from? Where did 75% CD come from?
What?
Where did 785% CD come from?
The L3 CD.
L3 has a value. I cannot remember how I initialized that. Yep, it's CD.
Oh, the value of the
So that's the other CD because of the dot byte at label L3. Say again?
We're just looking
Okay.
Why is CD not out? Why is CD not out? So things like that.
Why is CD here?
Yeah.
Because that's a dot byte. It's a single byte. There are no ordinary issues there. Okay.
L1 mode integer. So you move one space there, then that all then comes this way around it. Yeah, makes sense.
Just remember, little endian, least significant byte at the lowest address. Yep. Go ahead.
If we still be significantly to left, shouldn't be BC and BA?
No, because we do not swap within a byte. Remember, if it's within a byte, it's just AB. We don't swap the positions within a byte because we cannot address within a byte. So it doesn't matter whether it is stored in little endian method or big endian method. So getting back to the projector, let me go back to the spreadsheet here. This is big endian representation. This is little endian representation. Some processors use the big endian representation. The 68,000 processor family uses the big endian convention. I think the PowerPC is still big endian. I'm not 100% sure. TCPip is big endian as well. So in TCPip, when it needs to transmit a 32-bit number, it transmits the most significant byte first, instead of the least significant byte first. Okay. So that's why it's really a toss-up. Which one is better? Well, there's no real answer to that question because it's a toss-up. Okay. Either way has its advantages and also disadvantages. Are there any questions about this part of the lecture? Yep.
So there's no way to do like orders.
No, because memory with the i386 processor is byte addressable, not 4-bit addressable. So that's why when you specify an address, you are specifying the byte location, and you cannot specify anything smaller than a byte location because it is a byte addressable memory space. Any other questions? Okay, that's a good question. When are we done? Are we done yet? Yep.
L1 plus 5, push all the
If you do an L1 plus 5, let's take a look. So L1 plus 1, L1 plus 2, 3, 4, 5, 6. So 5 would be here. So the question now, my question to you is, if you want to do a move something, L1 plus 5, what is the width of the destination? It won't work if it's 4 because we have only allocated memory up to this point. If you specify a move L here, that means I want to copy, let's see, 1, 2, 3, 1, 0, 1, 2, 3, 4, 5. So that means 5, 6, 7, 8. I'll be trying to access 2 bytes over the boundary of what is already allocated. In the previous version of the assembler, it would actually do something here. You can still access it. But in the newer version of the assembler, it makes sure that the boundary is respected, so you cannot access beyond that point.
So you could essentially only start with L1 plus 3. That's as high as you could go and have a result.
And move 4 bytes at a time. Yes, with a move L instruction, you can only start with this one. That's the latest. That's the last byte that you can start.
And then would it print out CD 5, 6, 7, 8?
It will print out CD 5, 6, 7, 8, 1, 2, because this is the last address. This is the last byte to the highest address, so it becomes the most significant byte. But when we read a number, we read from the most significant digit to the least significant digit. So this number, in fact, will be CD 5, 6, 7, 8, and 1, 2. Yep.
So if we say move L2 into EAX, and we said L2 minus 2, would it be 1, 2, 3, 4?
Okay, if you do a L2 minus 2, this is L2, L2 minus 1, L2 minus 2, and you want to do a L2 minus 2, move it to where again? EAX? Okay, if you're moving into EAX, it's a 4-byte copy. So it will be copying these 4 bytes into whatever register you want to copy to, which will make this the most significant byte. So it will become 5, 6, 7, 8, 1, 2, 3, 4.
If you're moving to AB, that one right there to the AB1, how will it like? Which one? Okay, to go from going from to the AB register, then why you want to send that one?
Okay.
From the location L2 to the AB, the L1 plus 1, then why won't we have the L1 plus 1 value inside, and why will we have a 5, 6, 7, 8?
Can you repeat that question?
We want to change that one to 7, 8.
Are we changing the memory location, or are we changing where we started the copy?
The locations.
We're changing the locations?
Like if you do like L2 minus 2, L2 minus 2.
Okay, if we want to do L2 minus 2, then this is L2, this is L2 minus 1, and this is L2 minus 2. Yes, so what about it?
So where will it start from, I guess, the next space?
It depends on how wide you're copying, how many bytes are you copying. Remember, we can move byte, we can move word, we can also move long word. So depending on the width of the operation, we can be moving just 1 byte, which is 3, 4. We can be moving 2 bytes, which will be 1, 2, 3, 4. Or you can move in 4 bytes, which is 5, 6, 7, 8, 1, 2, 3, 4.
But it always says on the right. From the right, start from the right.
You start from the least address.
So can you what's it called when if you were to change L1 after start, like you were to do move L $, 6,000 EAX, like could you change it from being hexadecimal 1, 2, 3, 4 and change it after you've already started the program? Like, so once you get to start, and then like after all that stuff, then could you do move L and then put something completely new in there, comma, %?
You mean in your homework?
No, I mean just in general. Could you do that? And what's that called? Like, is that recasting the
So
bits?
you're talking about adding an instruction?
Yeah.
Move L. Let's go ahead and say it.
$500, comma, % EAX.
That will overwrite EAX with the 32-bit representation of 500.
Okay, so then the hexadecimal would print out whatever 500 is in hexadecimal then?
Right, in hexadecimal it's going to be 1 something because your 500 is less than 512, which is 200 in hexadecimal. So it's going to be 1 something in hexadecimal. It's going to be
would
1
L1,
F something.
But then would you still have L1, or would now L1, like if you were to, does that become the new L1 if you were referred
No,
to it
because
later?
the register is independent to memory, and so is your immediate operand. In other words, you can overwrite EAX, but EAX has no linkage to the memory location that you copied from earlier.
So L1 is still existent. If you were to then do move L1 EAX, would it revert it back to the L1?
Absolutely.
Okay.
Yeah. L1 is nothing more than a label, like a bookmark, to remember the location of this memory location.
So you can't overwrite it after you
You
start the
cannot
program?
overwrite L1. L1 is fixed. It's just a location in memory, and you cannot change it.
Okay.
Now the location or the bytes at that location, because we put those into data this time, those bytes can be overwritten if we use the move L $ something into L1. Yes, we can actually overwrite those locations.
Okay.
Question? Yep.
Okay, so you're using move L. So what if you use like move L or move W?
Move W?
Yeah, L1 plus 1, I guess.
Okay, if you use a move W, L1 plus 1 into a 16-bit register, that 16-bit register will get 3, 4, AB.
Not 1, 2, so it changes the hit.
Not 1, 2, because you started with L1 plus 1.
Okay.
Right? Did you say L1 plus 1?
Yeah.
Yeah.
So that's the W changes it.
Yeah, if you use a move W, L1 plus 1 to say register AX in this case, the register AX is going to get 3, 4, AB, but it will only affect the least significant 16-bit of EAX. So the most significant 16-bit of EAX remains unchanged. So you have to kind of keep that in mind too. Okay? Because you can overwrite only a portion of the 32-bit register when you use a move W or move B instruction. Right? Yep.
So can you use a move W to EAX, or does it have to be to?
If you use a move W to EAX, the assembler will complain because the width that you specify with the instruction is inconsistent with the width of the operand. Okay. Any questions? Any questions back there? Nope. Okay. So is that okay so far? Okay. So what I'll do is I will go give you a a cheat mode for this homework assignment. Yep.
Can you use like a multiplication? L1 multiply 2.
But you'll be multiplying the address itself, which doesn't make any sense, because you'll be doubling the location where you're reading from, but not the content at
Just
that
plus
location.
and minus, yeah. Just plus and minus.
Plus makes sense, minus makes sense, but not multiplication in this case. Yep. Okay, so here's the cheat mode of doing the homework assignment in GDB, because you can use the X command. Now the X command is really flexible, because what you can do is you can specify how many bytes or how many things you want to look at. Okay, so let's say we want to look at 3 things, and each each thing is a half word, which is 16-bit in this case, and I want to print each thing as a hexadecimal number. Then you can specify the address. Let's say we start with L1, and when you use the X command and you want to use a label to identify where you're starting, you have to use the percent or the ampersand symbol. Okay, this is a inconsistency between GDB's assumption and also the language that we are using to write our program. GDB makes an assumption that we are dealing with a C program, but we are actually not dealing with a C program. So it is misunderstanding what L1 is, or the meaning of L1. So we have to do it this way instead of just saying L1. Okay, so what this would do is it's going to print 3 things. Remember, the 3 is the count, the number of things. Each one is a half word or 16-bit, and then the X means which base do you want to use to print those values. So is that making any sense that it will print A, B, C, D, 1, 2, 3, 4, 5, 6, 7, 8? Because it's printing A, B, C, D as the first 16-bit thing, 1, 2, 3, 4 as the 16-bit thing next to it, and then 5, 6, 7, 8 as the next 16-bit thing next to it. So this is really useful because it helps you identify what if I look at this location as a 16-bit thing as opposed to 32-bit. Okay? There's another really super cheat mode in this case. The super cheat mode is to use 7BX, which means I'm looking at individual bytes, 7 of those, starting at location L1. So now we actually get the entire memory content out in the order as bytes, and it is identical to the one that I have presented here on the whiteboard. Yep, go ahead.
So the H is stating half bit?
Half word.
Or half word.
Yep, a half word in GDB is 16-bit.
So
a
basically,
word,
that command is allocating the size that you want it broken up into?
correct. It is determining the size that you want it. How big is one piece? A B is 8, a H is 16, a W is 32. Yep.
Okay. How is it cheating? Although you knew how it would look like that, if you make our own chart like that, we already knew what it would be. How is it cheating? What's so special about this thing that looking at that one, we already knew how it was looking at?
Because you don't have to do work.
Oh.
Okay. Because you don't have to think about it, right? But it is not going to work, in the exam because the exam is going to be a paper exam. So you still have to know how to do this by hand first. So that's why I said, do it by hand, do it on paper first, and then only use GDB as a verification tool and not use it as the tool to use to do the homework.
It's popular anyway.
Question. You said W was the
W is 32 in GDB. And that's why it's inconsistent, because when you specify move W, it means 16-bit, but when you in GDB, when you specify W in the X command, it means 32-bit.
So you could look at all of that with the W, it would look at all of it at once.
No.
Say again?
Only look at the first
If you were to do, like, it would just be WX at L, it would show you all of it at once. If you were to do X/WX at L1,
Then it would do
print
one.
everything.
No, the assumption is only one. But if you don't specify the count, the default count is 1.
But if you're specifying 32-bit, how much would it display the whole thing?
No, it will display,
Just the.
it will display whatever is at the location that you want to display. So if I specify just, WX, but without specifying a count, it would display one 32-bit thing and print it in hexadecimal.
Oh, okay.
And that's what it prints.
What if you were to do 2? Would it print the rest of it too?
It would, in this case, it's an interesting one. I think it might give me a segmentation fault because I really have only allocated 7 bytes.
Right.
And I'm attempting to read the 8th one, and it does, because I think the allocation boundary has to be a forward thing, has to be a 32-bit boundary. So that's why it has to allocate this one extra byte, but it's not actually initialized. And whatever it is 0, 0, but you cannot count on it being 0, 0. It is simply uninitialized.
Okay.
Yeah.
If you had done 3 there, then you can do the third one as all zeros.
Say again?
If you had gone like X, 3WX, even if you do all zeros.
Okay, so the question is, what if we change the count to 3 instead of 2? I think this will give me a segmentation fault. Oh, maybe not. We're basically dumping areas in the memory location that I have not allocated or initialized.
So why do we get one on that one? Why
Because
is
it's
that
not
there?
initialized. It's just random stuff there that is not something that I specified.
Okay, so if we had L1 is equal to 1, 2, 3, 4 ABCD, and we had L2 as 5, 6, 7, 8 ABCD, and then the L3 as F byte. So if we had like 2 ints and nothing for the half word or the W, and then 1 byte, so that would be alright too. Then like that.
It will just be contiguous. You can have a dot in, a dot word, and then another dot in, and then whatever. It doesn't matter.
Oh, that's fine.
A dot in allocates and initializes 4 bytes. A dot word allocates and initializes 2 bytes. A dot byte allocates and initializes 1 byte. Yep.
Can you use multiple ones at once, like do the W, do the V, and do the H, so you got each of those in their own variable?
No. Remember, there's no such thing as variables.
Or not? Well, like just like in their own like.
Yes, you can chain them. In other words, you're asking. Okay, let me get out of here and then go back to the source code. And so you're asking, can we get rid of L2 and L3 as label definitions?
Yeah, I just put them all in one.
Absolutely. That would be fine too. It will give you exactly the same memory layout. You just do not have this bookmark called L2 for convenience, and this bookmark called L3 for convenience.
So it's just for convenience, is why we have
Exactly. They're only there for convenience. In other words, in this particular case, if you say L2 minus 4, it is exactly the same thing as L1. Or if you say L1 plus 4, it is the same thing as saying L2. Exactly the same. There are no differences between those two expressions. Question? Okay.
You said something earlier about there not being types.
Yes.
But so what do we call these documents?
They are called directives. They're called directives. They're simply there to allocate memory from in this case, from the data segment and initialize. But it does not prevent your instructions to do something that's really awkward, like starting here and read across the boundary. In other words, the boundary that we think there's a boundary between the dot int and the dot word, that boundary is only in our head. The assembler does not see any boundary whatsoever. It's just one contiguous piece of memory and it is byte addressable. That's all the assembler sees.
So when we select one of those, it's gonna be just a certain, when we use one of those, it's gonna be a certain number of bits, essentially.
That is correct. You are basically controlling how many bits you are allocating for that particular value when you initialize memory. Yes.
So under L1 we had .n, .word, and .byte. So we did move L. Is that gonna only move the int part of
Nope,
it? or
nope, nope,
all
nope,
of
nope,
it?
nope. Your instructions or the with object instructions has absolutely no correlation whatsoever to how you allocate memory. In other words, you can be allocating 4 bytes using the dot byte thing and access all 4 bytes using a move long instruction. That is perfectly okay. Yep.
If I do like a move W, L1 plus 4, it would only point at 78?
You want to do a move W,
So
L1 plus 4 to
That'll be at 78?
so that the destination will get 5, 6, 7, 5, 6, 7, 8.
Yeah, move W. But move B, like move B.
Move B would just be 7, 8, because it's always moving from the byte that you specify. If it's a multi-byte in the specification, then it will go forward to the next and next and
Then
next.
that will become the value of EAX if you go in that function?
You cannot do a move W to EAX.
So move, so the, what's it called?
AX.
AX?
Yeah.
So EAX will have all, will be 32-bit no matter what.
EAX is a 32-bit view of that register. Yep.
So, a quick question about big Indian and little Indian.
Right. Go ahead.
If you were to not have L2 and L3, they're just completely gone from that. It would be 1, 2, 3, 4, A, B, C, D if you were to do it in big Indian.
Okay, where am I reading from? What
The
is
start of L1.
the start at L1, and you're trying to read it as a big endian number?
Well, like,
Or using a
let's
big
just
endian
say you
here?
had L1 and in your dot data, you had L1 dot end, and then you had 0x, 1, 2, 3, 4, A, B, C, D.
Yeah.
If you were to just read that back, what would it read? It wouldn't read to you C, D, A, B, 3, 4, 1, 2.
Okay, that's a good question.
wouldn't read it.
Because if assuming you're using the same assembler, and the assembler is assembling for that architecture, it already knows how to arrange the bytes in that particular endian list. In other words, if you use a big endian processor, or the assembler targets a big endian processor, it would have represented 1, 2, 3, 4, A, B, C, D as 1, 2, 3, 4, A, B, C, D, because that's how those bytes should be organized in memory.
So let's say you were to do examine /4 VX at L1.
Uh-huh.
How would that read it back?
For a big endian
For this
processor?
right here even.
But assuming we're targeting a big endian processor? Or
Okay,
are we
yeah.
assuming we're still targeting the little
Either
endian
one.
processor?
Either
Okay.
one. Or give
This
it
is
both.
how it will look like when the assembler targets a little endian processor, because CD is the least significant byte, it has the lowest address. Now, if you use the assembler for the 68,000 processor, which is a big endian processor, if you do the same thing, x/4bx, ampersand, L1, then you would have read 1, 2, 3, 4, A, B, C, D, because the assembler allocates and initializes memory according to the endianness of the target processor. And we are, in this case, we are targeting a little endian processor, and that's why it is arranged for that purpose.
Now, when you convert it to
Okay. Okay.
So, going off of that, if it was arranged in big Indian, would that second answer be the answer you would get?
The second answer,
Yeah.
if it were a big endian processor, then the second answer would be correct. Yes. Yep.
If you don't have like L1, just complete 0, 0.
If I do not have an L1, then I would have a hard time referring to that location,
Like
because
zero?
I need
First
no,
location,
it's
no?
not at location 0.
Wow.
It is not at location 0 because, okay, let's go back to GDB, so we can actually take a look at the location. So if you go back to GDB, you can actually say print ampersand L1, and okay, we have to. I just ran GDB without a command. Fine. Okay. So if you print ampersand L1, which is the address of L1, it is non-zero. This is the start location of label L1. That's actually the location. In other words, in this particular case, because now I know what L1 is, I could have said, move L 0x4804992.
So we need
and accomplish the
at
same.
least one location, one label. We need
Correct.
To have
We only need one label because from one
At least
label
one.
we can do an addition or subtraction to get to wherever we need to go. Yep. Are there any other questions? Well, go ahead.
What does data variable mean in this line?
It thinks it's a data variable, but it's not. It's doing a typecasting. If you recognize the syntax, it's basically okay. Let me just highlight the portion so we know what you're talking about. Okay, when you do this in C, it is taking the address of something, right? And it's taking the address of L1 in this case. Now, because we are writing a program in assembly language, there's no such thing as type. So that's why it doesn't know the type of it at all. And that's why, when it uses this representation, it's trying to tell me what is the type of the value. But since there's no type information, but we know it's an address of something, so that's why there's an asterisk here to basically say, well, we know it's an address of something, but I have no idea of what type it is.
Okay.
So it's trying its best to guess what it's a pointer to what, but it cannot know because there's no such information in the debugger. I mean, in the the symbol table. All right. Any other questions? Well, technically speaking, you guys have all the pieces that you need to do the homework as of now. Let me just double check, with my description of the homework, just to be sure. And this is the part we talked about, the little endian processor architecture, which is the least significant byte has the lowest address. Okay, so that would be the important part. We talked about the X command, okay, the cheat code, okay, X/7XB, and so on. We talked about the print command being useful to print a register in any base that you want. Okay, you can print it in binary if you want to. We talked about memory allocation using .in, .word, and .byte in assembly language is contiguous. We talked about there's no such thing as a variable in assembly language programming, which means you can cross the border or you can cross the boundary of allocation and nobody cares. Okay? The processor does not care, the assembler does not care, GDB does not care. Okay? And you can perform arithmetic operations on labels, L1 plus 1, L2 minus 2, and so on. And also, one last thing, you can overwrite a portion of a 32-bit register depending on the target register. In other words, okay, I'll just use this as an example. If I do a move L1 to %EAX first, and then I do a move B, let's say L2 to %AH, what would be the result after this? Do it on paper first. Okay, remember, do it on paper first, and then use the assembler or the debugger to verify your answer. So in this case, EAX after the first instruction, EAX will have just 1, 2, 3, 4, A, B, C, D in hexadecimal. Is that okay? Okay. The second instruction is going to copy whatever 1 byte from wherever L2 is. L2 is right here. It has a content of 78 in hexadecimal. It uses that to overwrite AH, which is only bit 8 to bit 15 of EAX. So that means this byte is overwritten by 78. So this is the trick, because you can overwrite only a portion of a 32-bit register depending on which portion you are writing to, without affecting the rest of the entire register. So you need to use that trick also to do your homework. Okay. That is correct. If I change this to AL, it would have overwritten the CD, so it becomes 7A. Okay.
Why did you overwrite this when I provided? It's only done in the L. like come here, like why like when that one be like a separate L1, L2, and L3? Why did you override this one? Why didn't you make 1, 2, 3, 4, A, B, C, D, and then 7, 8 next to it? Why did it place the things in the L, E, S? Why is it? It just seems the E, S.
Because that's what the instruction specifies. It specifies EAX as the destination of the first instruction, and AH, which is this portion, in the second instruction. AH is a part of EAX.
Okay. Oh, okay. One thing. So you can change, like we're gonna change A, B, C, D, like by by giving you the instructions. Like if there's any way you can change 1, 2, 3, 4. Because remember when we did yesterday, we
We answered that question last time already. There's no way to modify. Just the most significant section is allowed. All right. So are you guys feeling confident you can get it done by tonight?
When is it due?
Sorry?
When is it due?
It's due in a week, which means most of you will probably procrastinate until next Wednesday. And the recorder is